Hello physics students. This is the problem that we left off on in class last time, so we're going to pick back up here. Example 1.9, launching a weather rocket. Use the first two steps of the problem-solving strategy to analyze the following problem. A small rocket, such as those used for meteorological measurements of the atmosphere, is launched vertically with an acceleration of 30 meters per second squared. So it's launched vertically, has a positive acceleration, so it is accelerating vertically. It runs out of fuel after 30 seconds. Okay. What is its maximum altitude? So I think what we have to think, we know that when it has the fuel, that it is accelerating. The engine's going and it's causing this acceleration that we've been told about. What happens when the fuel's gone? The engine quits working. It stops accelerating that thing like it was. What happens then? Does it immediately then begin to fall or descend? Think about that for a second. When it stops accelerating from the engine, it doesn't immediately begin to descend. It continues upward, but instead of having a positive acceleration, it has a negative acceleration. It had a velocity. When that acceleration stopped, when it stopped being accelerated, it still had a positive velocity. Pretty significant positive velocity. So it continues to have that positive velocity upward, but that positive velocity begins to decrease because of the negative acceleration due to gravity, the force of gravity. So let's say if it was going 300 meters per second when the acceleration stopped, then after another second it might only be going 200 meters per second. After another second it might only be going 50 meters per second. And till eventually it will finally reach its highest point that it will have gone, and then it'll begin to descend. But we just want to know in this problem, what is its maximum altitude? And notice that we're only told to use the first two steps of the problem-solving strategy, which was given back in this previous slide. So what are the first two steps? To model. So maybe we want to treat this object as a particle, like a point, that we can more easily draw the situation, draw a motion diagram for the situation, and then visualize that thing by drawing that motion diagram. We may even, after we draw the motion diagram, want to use a graphical representation, like a position versus time graph might be good for us to use. We haven't talked a whole lot about those, but we've talked a little bit about it. So if I'm drawing a motion diagram for this rocket, okay, here's the ground. I don't have my stylus, so I'm drawing with my finger, so the drawings may not be very good. But at time 0, the rocket is here. All right, it's accelerating upward, so at time 1, maybe it's here. At time 2, it's here. At time 3, it's here. Okay. Let's just say right there it runs out of fuel. So then, at time 4, it might be here. At time 5, I think I may be out of space. Alright, because I had run out of space, I minimized my drawing here to make it a little smaller and shorter. So let's just say at this point, this highest point here, it runs out of fuel. So then maybe the next point, because it begins to have a negative acceleration, is closer than these last 2 points were. So maybe right here, and then right here, and then right here. And then it begins to descend. So, and maybe I want to make a mark. Maybe I want to make a note right here and say right here is when the fuel ran out. So no, again, I can't write with my finger very well. Okay, so at that point there's no fuel. Alright, that is one way we could do that first and second step. Another way might be if I do a position versus time graph, y and t. The first position is going to be at 0 at time 0. Then it goes to some higher altitude at time 1, but then the next altitude is going to have gone over a greater displacement of altitude, and then even greater displacement of altitude at the next time. And so this is like that is actually going to be modeled by parabola that opens upward. All right. But then it begins to have a negative acceleration, so that next altitude won't be as much, and then won't be as much again. So then that's going to be represented by an upside down parabola, flipped parabola. So we have to, and again, we might say right here is where there was no fuel. All right, and so we're looking for that highest altitude. That's what we would be trying to find. And so that pictorial representation gives us a good feel for the problem and what exactly we're trying to find and how it relates to what is going on in the rest of the problem. All right, and you can see here, this is the drawing from the publisher. It says that it has a positive acceleration here. Here's where the fuel ran out, has a negative acceleration, and then here's where it finally finishes its upward motion. And then it also drew it with like a drawing, but that doesn't really help us, I don't think. It did not do a position versus time graph, but I think a position versus time graph can be helpful there. All right. Units. Science is based on experimental measurements, and measurements require units. The system of units in science is called Le Système International des Unités. You got to say that with some kind of an accent. I don't know what kind of accent that just was, but some kind of an accent. Or SI units. The SI unit of time is the second, abbreviated S. This is kind of interesting. How is a second defined? That is the real trick. Not just deciding on a unit, but figuring out how to define that unit in a way that doesn't change, in a way that will remain constant for the foreseeable future, so that people everywhere at all times will be able to recognize that definition. So here's how a second has been defined. It's been defined as the time required for this many 9,192,631,770 oscillations of the radio wave absorbed by a cesium-133 atom. Isn't that crazy? I mean, but I mean, they kind of had an idea what the second was before they, in modern times, defined it this way. So they just figured out a way. They say this happens the same amount of time all the time, so we're going to define it this way. And here's a picture of an atomic clock at the National Institute of Standards and Technology, and that is the primary standard of time. The SI unit of length is the meter, abbreviated M. How is that defined? It is the distance traveled by light in a vacuum during 1/299,292,458 of a second. So they define the unit for distance by light, by the speed of light, and by the second also, which was defined before the unit for distance. So the unit for distance depends on the unit for time. That's already been defined up here. And the speed of light was a good thing to use because it's constant. The speed of light is constant, but the most they had to say in a vacuum. So light's going to go the same distance every time a particular unit of time passes by. All right, more SI units. The SI unit of mass is the kilogram, abbreviated kg. This is the one that's been the toughest to get a good standard for the scientific community. Right now, here's the definition, but they're constantly trying to figure out a different way to define kilogram. 1 kilogram is defined as the mass of the international standard kilogram, which is a polished platinum iridium cylinder stored in Paris. So they don't want to have definitions for these units that are physical things. Like, that's why they use the speed of light, because it's not a physical thing that can be affected over time. That's why they use the radio waves of or whatever for a second, because it's not a physical thing that can be affected by deterioration over time, decay or whatever. There is a platinum iridium cylinder that's stored in a big crazy vault underground in the city of Paris that defines what a kilogram is. It is the kilogram. It is the only thing in the world, it is the only thing in the universe that truly is a kilogram. They made copies of that thing. In fact, I'm going to send you out a video about this, which is really interesting. But they made copies of it and sent those copies out to various countries in the world to be stored as well. Then after like 50 years or 20 years or whatever, they brought them back in and compared them, and they weren't all the same as far as their weights. Now, it was, way down the line of decimal places that they were off, but still, over time, that's going to get worse and worse. And even this kilogram right here, is undergoing change of some sort, entropy of some sort. So, anyway, that's why they're constantly trying to get a better way to define the kilogram. And there have been lots of proposals that have seemed promising. And I would think that in our lifetimes it will be defined a different way. A long time ago, it was defined by the mass of a liter of water. And I actually kind of like that definition. But anyway, if we're going to have a physical definition, and I think it was the mass of a liter of water at sea level or something like that. All right. Many lengths, times, and masses are either much less or much greater than the standard of a meter, a second, and a kilogram. Now, let me say this too. I forgot to say this. The kilogram is the only standard unit that has a prefix. Notice the meter doesn't have a prefix. The second does not have a prefix. So why is the unit for mass, why does it already have a prefix on it? Why wouldn't it just be the gram? It's just having to do with the history of this unit. They started out with something called the gram, but then for some reason they made that really small later, and so because it was really small, then they realized, oh well, I think it would be better to have a standard that was bigger than that. Then they actually made the standard be 1,000 of those grams, and so they had to call it, since they already named the gram, they had to call it the kilogram. So the standard unit for measuring mass is the kilogram. All right, we use prefixes to denote various powers of 10, which makes it easier to talk about quantities. So, like, when something is much, much smaller or much, much greater than these units, that's when we use these prefixes. So we might use the gigameter or the kilometer or kilometer, depending on how fancy you want to sound, or the nanometer or a nanosecond or something like that. And here's what those things mean. Those prefixes means multiply that 1 in front of that unit by 10 to the 9th or 10 to the negative 6th or whatever. And it's that much of a unit of the unit. Unit conversions. It is important to be able to convert back and forth between SI units and other units. So here in the United States, we use English units, kind of for our day-to-day lives. There was a big movement when I was growing up to get the United States to transform over to SI units, but there was a big public resistance against that, and so it never happened. I think it probably would have been good for it to have happened, but this is where we are. I remember, interestingly, when I was probably like 5 or 6 years old, there was a space shuttle that was launched. It was a very famous launch called the Challenger space shuttle. And it was very famous because it carried not just astronauts, it carried some regular individuals that for the first time normal citizens would be carried into space. They had like a teacher and a doctor and some other regular folks from various countries. And there were multiple countries involved in this. I think the U.S. and Russia were two of the big ones. And we all watched that on TV when that happened. And when it was launched, about, 20 seconds after the launch, when it was up in the air, it blew up. And that was just a tragic moment for the world to see that. And I remember that there was it was said that the reason that happened was because there was something in the space shuttle that had gone wrong due to the fact that there were multiple countries working on this project collaboratively, and there was a unit conversion mistake made, which made something go wrong and haywire in that machine. And so that again fueled the movement to move the U.S. to international system of measurement. But then it was kind of said, well, that's just a rumor. That wasn't true. That's just using that situation to try to further that goal of some. And so anyway, that was just a really interesting time. And obviously we didn't go over to the international system of measurement here. But we want to be good at converting at least. If we're not going to use the international system of measurements, then we better be really good and adept at converting between the two. So here, 1 inch is now defined. It's not just equal to 2.54 centimeters. It's not approximately equal to 2.54 centimeters. That's just rounded off to the hundredths place. The inch is now defined as 2.54 centimeters. So that the inch, so that the unit of length in the English system is dependent on the international system of measurement, which is a good thing. So then if an inch is defined that way, and inch defines feet, and feet define miles, then a mile would also be defined by the international system as well. And then miles per hour. We actually do use the same units for time, don't we? The second is the same in both English and international system. There are a few conversion factors. The only one that I keep in my head is this one, the first one, the inch being defined as 2.54 centimeters. Because that's the one I have memorized. I don't have any of these others memorized. But if I just have that one memorized, I can always just do math and derive these others. Like I can convert any length situation if I just remember that. So one effective method is to write the conversion factor as a ratio equal to 1, because multiplying by 1 does not change a value. These ratios are easily used for unit conversions. Hopefully you've done this in some previous classes. For example, to convert the length 2 feet to meters, we will use the ratio 2.54 centimeters over 1 inch, because that's something equal to itself, something divided by something that's equal to itself, which would just be 1. so it doesn't change the value when that's the case. What I usually do is something like this T-chart, which is basically effectively doing the same thing that this calculation down here is doing, but mine usually looks like this. I'm saying 2, come on, why isn't it writing? 2 feet. Okay. And then I'm trying to, what am I trying to convert that to? To meters. So I'm going to say 1 foot, 12 inches. So the feet cancel. And then 1 inch 2 is to 2.54 centimeters. Again, I apologize for the really terrible writing, but it's the best I can do. And then we will say, I'm out of room, hold on. And then we need centimeters to be on the bottom here, and we're trying to get the meters. So if I want centimeters on the bottom and meters on the top, then it's going to be 100 centimeters on the bottom to 1 meter on the top, and my centimeters cancel, and I'm left with meters, which is what I want. And then everything on the top gets multiplied, everything on the bottom gets divided. So like in your calculator, you may want to say 2 times 12 times 2.54 divided by 100. Now, if there was more than one number on the bottom to divide by, then you may have to use some parentheses, like use parentheses, open parentheses, 2 times 12 times 2.54, close parentheses, divide by button, open parentheses, and then it would be like whatever's multiplied on the bottom. Let's say if it was a 10, 10 times 100, close parentheses, so that you're dividing by that whole denominator. Another way to do it would just be to hit the divide by button every time there's a number on the bottom. So let's say that if there was a 10 on the bottom, you'd say 2 times 12 times 2.54 divided by 10 divided by 100. That would also work. All right. At any rate, what you get there is 0.610. Notice how they put 10 to the negative 2 meters is 1 centimeter. That's the same thing. The 10 to the negative 2 is the same thing as putting a 100 on the bottom of that fraction, which is what I did. But either way you want to think about that is fine. All right, when problem solving, it is important to decide whether or not your final answer makes sense. For example, if you're working a problem about automobile speeds and reach an answer of 35 meters per second, is this a realistic speed? All right, so it says the table shows some approximate conversion factors can be used to assess answers using 1 meter per second equaling about 2 miles per hour. So if you said, okay, it's about 0.5 meters per second is a mile per hour. So 1 meter per second would be about 2 miles per hour. Then you find that 35 meters per second is roughly 20 miles per hour. I guess maybe 17.5 or something like that. But anyway, a reasonable speed for a car. So yes, if you reached an answer of 350 meters per second, this would correspond to an unreasonable 700 miles per hour, indicating that perhaps you made a calculation error. I am noticing, now that I'm looking at it, that there is an error in this slide. There is definitely an error here. If 1 meter per second is 2 miles per hour, then every time you have a meter per second, you would have 2 miles per hour. So 35 meters per second wouldn't be roughly 20 miles per hour. It would be roughly 70 miles per hour. So I don't know if I can edit this presentation or not. Okay, I was able to figure out how to edit it, so it should be right from now on. All right, it's important in science and engineering to state clearly what you know about a situation, no less and no more. Again, hopefully you've experienced these concepts in a previous science class. but we'll go over it again. For example, if you report a length as 6.2 meters, you imply that the actual value is between 6.15 and 6.25 and has been rounded to 6.2. Whatever the last number is, you're kind of, the assumption would be that there was one more decimal place there that was rounded to get that 2. The number 6.2 has 2 significant figures. More precise measurement could give more significant figures. The appropriate number of significant figures is determined by the data provided. Calculations follow the weakest link rule. The input value with the smallest number of significant figures determines the number of significant figures to use in reporting the output value. I like that. That's really good. That keeps you from overstating your case, which is the tendency for everybody, especially scientists, is to overstate your findings. But using the weakest link rule keeps you from doing that. It makes you say, this is, I can't say that it's any more precise than this because this was the weakest link in my calculation. All right, determining significant figures. Leading zeros locate the decimal point. They are not significant. So zeros that come before other numbers are not significant digits. But zeros that follow the numbers are significant digits. It's saying, I didn't just get this 0 because I rounded. This actually came out to 6.20 units. All right, so it says the number of significant figures is the number of digits when written in scientific notation. So if you write this thing in scientific notation, you want to put the decimal point after the first significant figure here. So you put it here, 6.20 times 10 to the negative third. A trailing 0 after the decimal place is reliably known. It is significant. The number of significant figures does not equal the number of decimal places. Changing units shifts the decimal point but does not change the number of significant figures. All right, so in other words, when we, let me just say this. When we are converting using this right here, the 2.54, we would not even count that as part of our significant figure determination, because this is defined this way. This would be equal to 2.54 0.0000, as many zeros as you want to think of. So really, this conversion has an infinite number of significant figures. So that does not, the conversion factor does not affect our significant figures at all. All right, using significant figures. When multiplying or dividing several numbers or taking roots, the number of significant figures in the answer should match the number of significant figures of the least precisely known number used in the calculation. When adding or subtracting several numbers, the number of decimal places in the answer should match the smallest number of decimal places of any number used in the calculation. So it's a little bit different rule when you're multiplying, dividing, exponentiating, taking roots. You think of significant figures when you do that. But when you are just adding and subtracting, you don't have to think of significant figures. You just need to think of the decimal places. All right, exact numbers are perfectly known and do not affect the number of significant figures an answer should have. Examples of exact numbers are the 2 and the pi in the formula circumference equals 2 pi r for the circumference of a circle. So the 2 and the pi don't affect the significant figures. Only the radius, the preciseness of the measurement of the radius, only that would affect the number of significant figures that would be acceptable in the circumference. It is acceptable to keep 1 or 2 extra digits during intermediate steps of a calculation to minimize rounding errors, as long as the final answer is reported with the proper number of significant figures. So you want to keep while you're doing your calculations, you want to keep the numbers as many decimal places as is reasonable to work with. You want it to keep it as precise as possible. Keep a lot of them. Keep a lot of decimal places until the very end. When you finally get your final answer, then put it in the correct number of significant figures. All right. Examples and problems in this textbook will normally provide data to either 2 or 3 significant figures, as is appropriate to the solution. The appropriate number of significant figures for an answer, remember, it is determined by the data provided, or by in other words, when you're working a physics problem, use the same number of significant figures as the numbers that are given to you. It's determined by the numbers given to you in that problem. Example 1.1. An object consists of two pieces. The mass of one piece has been measured to be 6.47 kilograms. The volume of the second piece, which is made of aluminum, has been measured to be 4.44 times 10 to the negative fourth meters cubed. A handbook lists the density of aluminum as 2.7 times 10 to the third kilograms per meter cubed. What is the total mass of the object? All right, so we're told that this object has two pieces, and we're told the mass of the first piece. So the mass, let me see, why is it not writing? All right, hold on. All right, the mass of the first piece is 6.47. We want to know the mass of the second piece and add it to the mass of that first piece to get the total mass of that object. So we are given that the volume, we're given volume, and we're given density. All right, so density, how does density relate to mass and volume? Density equals mass divided by volume. So I can use that to figure out the mass because I'm given the density, I'm given the volume, the mass will be the only unknown. So the density is 2.7 times 10 to the third. And notice it's kilograms per meter cubed. And notice that the volume is given to me in meters cubed, so that's good. That's consistent units. If the volume was given to me, let's say in like centimeters cubed, I would have to convert that to meters cubed before I could do this, or I would either have to convert this over to centimeters cubed. They have to be consistent. All right, so this is kilograms. I'm just going to do some unit analysis here. Per meter cubed equals the mass divided by the volume, which is 4.44 times 10 to the negative 4 meters cubed. Okay, so what do I do to solve for mass? All right, I multiply by 4.44 times 10 to the negative fourth on both sides. All right, so times 4.44 times 10 to the negative fourth meters cubed on this side, which cancels out, and times 4.44 times 10 to the negative fourth meters cubed on this side. So notice that the meters cubed cancels out, and we're going to be left with kilograms, which is exactly what we want when we're trying to find mass. So the units work out perfectly, as they always should. And so I'm going to multiply the 4.44 with the 2.7, and the 10 to the negative fourth with the 10 to the third. And hold on, let me calculate that. All right, we get 11.988 when I multiply the 4 with the 2.7, and the 10 to the negative fourth and the 10 to the third ends up with 10 to the negative 1. And then I would like to put this in proper scientific notation. So it's 1.1988. Since I moved the decimal point one place to the left, I balance that out by, so in other words, I made this number smaller. I got to make this number bigger. I made this number smaller by a factor of 10. I got to make this number bigger by a factor of 10. So that's going to be times 10 to the first. Actually, times 10 to the 0. And 10 to the 0 is just 1. So that's just 1. So this is, and now I'm going to think about my significant figures because I'm done calculating. I had 3 significant digits in the 4.44. I had only 2 significant digits in the 2.7. So 2 significant digits is the limit. So this is going to be 1.2 kilograms. That's M2. So my final answer for the total mass of that object is going to be 6.47 plus 1.2, which is going to be 7.67. But I need to use, now that I'm adding, I want to use the least number of decimal places in, whichever number has the least number of decimal places. I need to have that number of decimal places in my answer. So I think I've got to end up with 7.7 kilograms as my final answer to the proper number of significant figures. Alright, and if we look at the solution from the publisher, that is exactly what we get. And you can read their explanation here, which is a good explanation. Alright, there are only a few slides to go, so I'm going to keep going here and finish. Orders of magnitude and estimating. Suppose you see a rock fall off a cliff and would like to know how fast it's going when it hits the ground. By doing a mental comparison with the speeds of familiar objects such as cars or bicycles, you might judge that the rock was traveling at somewhere around 20 miles per hour. This is a one significant figure estimate. Such an estimate or calculation is called an order of magnitude estimate. An order of magnitude estimate is indicated by the symbol, this thing, which I think is a tilde, which indicates even less precision than approximately equal, which is the double tilde here. So this double one is approximately equal to, where this is just an order of magnitude. This is somewhere in the ballpark of this. Alright, you would say that the speed of the rock is, V is somewhere around 20 miles per hour. Here are some approximate lengths in orders of magnitude. Length of a fingernail, 0.01 meters. Width of a textbook, 0.1 meters. Length of your arm is about a meter. Length of a classroom, maybe 10 meters. Length of a football field, around 100 meters. Distance across the campus might be 1,000 meters. Altitude of a jet plane, maybe 10,000 meters. Again, those are just orders of magnitude. They're not trying to be anywhere near something like precise. Orders of magnitude for masses. A raisin, 1/1000th of a kilogram. A pencil, 1/100th of a kilogram. An apple, 1/10th of a kilogram. A science textbook, about a kilogram, especially our big textbook. Medium-sized dog, 10 kilograms. Large human, 100 kilograms. Small car, 1,000 kilograms. Quick check 1.11. Rank in order from the most to the least the number of significant figures in the following numbers. For example, if B has more than C, C has the same number as A, and A has more than D, you would give this as the answer. B is greater than C, C is equal to A is greater than D. So the greatest one comes first, and the least one comes last. Alright, let's talk about it. A has two significant figures because the two zeros at the end don't count as significant figures unless they were to the right of the decimal point. If you were to write this in scientific notation, it would be 8.2 times 10 to the third. The thing is we don't know if those two zeros are significant or not, so we have to say that they're insignificant. If you did want them to be significant and you wanted to show that, you would write it in scientific notation 8.200 times 10 to the third. Then if they come after decimal, then they would be significant. Alright, B is only two significant figures. Also, zeros that come before the other numbers are not significant. If they were between numbers, they would be, but if all the zeros come before other numbers, they're not significant. So the 5 and the 2 are the only significant figures. So A and B are equal. C is three significant figures because 4, 3, 0 all come after the decimal point. A zero that comes after the decimal point and after the other numbers is significant. This is telling us that it actually goes all the way to that, or you wouldn't need to put that zero. So the fact that you didn't need to put the zero, but it's there anyway, means that it's significant. See, these others you had no choice but to put the zeros, so you don't know if they're significant or not because you had to put them anyway. This one you put it for a reason because it's significant. All right, D. So C is tied with, no, C is greater than A and B. And then D finally is 4 significant figures. 4.321, all of them are significant. So let's see, D would be greater than C, which would be greater than A and B, A equaling B. So it looks like choice A is the answer. And that is the answer. See how they say that those two zeros are ambiguous. So we just have to say it's only 2 because we can't tell anything greater than that. All right, chapter 1 summary. Talked about problem solving. We had a little problem solving strategy here to model it, to visualize it with motion diagrams and graphs. Then we solve it using mathematical representations of what's going on, like solving an equation. And we'll talk about equations that we're going to use later. Then we assess our answer to make sure it makes sense. Is it the right number of significant figures and all that jazz. Motion diagrams, we talked about those. Little summary of that. You can feel free to pause and read that. The particle model, where we just represent the object as a single point. And we're talking about position, velocity, and acceleration. Position locates an object with respect to a chosen coordinate system. The change in position, remember, is called displacement. Velocity is the average velocity is the displacement over time. It's a change in position over the change in time. And you can use vectors to represent these things. There's position vectors. There's different variables that might be used. R might be one of them. For velocity, V might be used as that. Acceleration is the change in velocity divided by the change in time. Use that vector usually as an A. An object has an acceleration if it changes speed or if it changes direction, which we're going to talk about later. So a change in the direction of the velocity, even if it's not a change in the magnitude of the velocity, is still a change in velocity. So that therefore there would be an acceleration. Some important concepts here. Pictorial representation, motion diagram, establish coordinates, define the symbols, list the things that are known, and identify what you don't know yet and what you're looking for. All right, that's in chapter 1, which is a basic introduction to a lot of concepts we're going to use throughout the course. See you next time.